Okay, welcome to lecture 11. Um, in this lecture, we are going to talk about Lagrangian relaxation and its augmented version, augmented Lagrangian relaxation. Um, so a few lectures ago, you learned how to identify to see if your problem is decomposable or not, if it has complicating variable or complicating constraint. If you have complicating variable, you'll learn how to implement Bender's decomposition. But in case you have complicating constraint, then Lagrangian relaxation and augmented Lagrangian relaxation could be a good candidate to be used. So hopefully after this session, you will be able to explain or understand, explain how Lagrangian relaxation, augmented Lagrangian relaxation, and alternating direction method of multipliers, they work. Throughout this lecture, I will use abbreviations, LR for Lagrangian relaxation, ALR for augmented Lagrangian relaxation, and ADMM for alternating direction method of multipliers. And hopefully you will manage to implement this techniques to a stylized model case study. So if you have optimization problem decomposable with complicating constraints, the typical classical, or let's say the first alternative you have is LR, Lagrangian relaxation. In the literature, this technique has also been known as a standard Lagrangian relaxation in contrast to augmented Lagrangian relaxation or conventional Lagrangian relaxation. Also, it's called as dual decomposition, right? Dual decomposition. While also techniques like Bender's, they are called as primal decomposition. Any clue why we call Lagrangian relaxation as dual decomposition while Bender's and similar techniques as primal decomposition? Any clue? Any guess? The reason is that in Bender's, what we are updating over iterations, it's the primal variable, the complicating variable. While here in the dual decomposition or Lagrangian relaxation, what we are updating over iterations, they are dual variables. Good, exactly. Sebastian and Kelly also, they mentioned the right answers. Also, we will talk about ALR. For ALR, you will see why we need a bit more techniques. So if we formulate our problem in augmented way, then we need to use different techniques that I'll mention, like auxiliary problem principle or ADMM. So ADMM is not a different technique. ADMM is a solution technique if we go for augmented Lagrangian relaxation. I'll explain what it means. But Lagrangian relaxation and its augmented version is not the only approach to decompose a problem when you have complicating constraint. For example, Danzig-Wolf decomposition also is an approach to decompose the problem. Sometimes it's very relevant if you have complicating constraints. So in this course, though it was a part of the course in the previous versions of the course 2-3 years ago, but I eliminated that part, Danzig-Wolf decomposition. But I'll talk about it in the next slides. I'll tell you about you. Also, I will not use APP in this lecture, though I will tell you roughly what the main idea is. Potential applications in power systems. A slide that I just added 1 hour ago. Okay, I forgot to update my slides actually. Okay, let's have a break of 2 minutes. I need to update my slides. Just a break of 2 minutes. Okay, I'm back. Well, So potential applications in power systems. I got this paper, an email from my colleague today, saying that saying that there is a new paper by from the groups of Bill Hogan, Karamanis, and Andrianisis, right? It's about the applications of dancing wolf decompositions for computation of convex Hull pricing. We talked in I think lecture 3, if we have binary variables, if we have unique enlightenment problems, we have difficulties about pricing. So one approach was uplifting, but the other approach that nowadays is very interesting, and I mean, it's a hot topic in mostly in US markets, it's convex hull pricing. And this is a paper that they use dancing wolf decomposition for convex hull pricing. So when I saw this paper today, um, well, I was thinking why I eliminated dancing wolf from this lecture, from this course. Yeah, that's well, but then if I added dancing wolf, then the lecture, I mean, the course could be yeah, extended a lot. Um, but I think since you learned Bender's decomposition and you will learn Lagrangian relaxation, it will be easy for you to understand, to learn what dancing wolf is. And there is a book chapter in this book talking about dancing wolf. It's a yeah, very well written book chapter. You can read and learn about dancing wolf. So in this course, I'm not going to talk about dancing wolf, but just for your information, it's also very efficient technique sometimes when you have complicating constraints. Good. Let's get back to our own business. So what kind of applications we have in power systems? Just a few examples. For example, you saw in previous lectures that the power balance equality, the ramping limits, they are good candidates to be counted as complicating constraints when we clear the market or when we solve optimal power flow problem, because if we relax them, we can decompose the original problem by agent or even by hour. So that's one typical, let's say, application. Or for example, if you think of multi-regional market clearing problem, let's say we have two regions like, I don't know, Denmark and Sweden, and they are connected only through, let's say, one town line, right? So there is a constraint related to power flow over this tie line. And if we relax it, then the market clearing problem or OPF problem, optimal power flow problem for region A and B can be solved separately. So then we can decompose the problem by region. If we do so, then we can call that we are clearing a distributed optimal power flow problem or distributed market clearing problem. Even you can think more, for example, you can say that in a distribution system, we have a radial system. Also, for example, you can decompose your problem by node. So it's a nodal decomposition if you relax the constraints representing the power flow between the nodes, right? So if you think, you will see that the Lagrangian relaxation or dancing wolf or any technique which is suitable for decomposable problems with complicating constraints, you can use, I mean, there are a broad applications. And remember, if you have complicating variable, you can take the dual problem of that problem, then you will have complicating constraint. Again, you can use Lagrangian relaxation or its variants, like augmented Lagrangian relaxation, ADMM, or even you can use dancing wolf. Any questions so far? Good. Again, my main reference is the composition book that I already mentioned. Also, there is a very nice long paper by Stephen Boyd et al. Published in 2011 that also is a main reference for this lecture. Good. Let's give some background about LR. The theory of LR, Lagrangian relaxation, and also its augmented variant was firstly developed for problems with continuous variables. and functions, and the problem with the objective function with first derivative continuous. It means that we have continuous objective function, sorry, continuous problems without binary. And if our objective function has a continuous first derivative, it means that if we take the first derivative, the problem, the terms is still continuous. It's not constant. For example, the objective function is quadratic. While if objective function is linear, the first derivative is not continuous, it's constant. We will talk about that. So, however, also in 1990, in 90s, the people, they used this theory for also for milk problems with problems with binary variables like unit commitment, and sounds that also LR worked very well. Though there might not be a proof of convergence, but sounds that in applications it works fine. So in general, Lagrangian relaxation, it works efficiently if the number of complicating constraints is relatively low. And it seems that as a heuristic, it works well if we have binary variables. So as I said, Lagrangian relaxation extensively used in 90s to solve unit commitment problems. For example, there are several papers by Professor Russ Baldick from University of Texas at Austin using LR for solving unit commitment problem, relaxing, I don't know, ramping constraint, balancing constraint, and you can find them in the literature. So in the case of Lagrangian relaxation, in addition to convexity, to make sure that, to guarantee that we will get convergence, the objective function of the original problem needs to be smooth or continuously differentiable. It means that we should have continuous first derivatives. In other words, I mean, the objective function needs to be at least quadratic, right? So if our objective function is quadratic while convex, right, then LR, I mean, we have a guarantee of convergence to global optimality if we use LR. Later, not now, but later, especially in the case of ADMM, I'll provide more references that also we may need more requirements to make sure ADMM will converge to global optimality, like Lipschitz continuity. I'll provide slides, some inputs later. So if our objective function of the original problem is linear, then that's why we need augmented version of LR, Lagrangian function, Lagrangian relaxation. So as summary, if our original problem has a quadratic objective function, it means that its first derivative is not constant, then we can go for LR, simple dual decomposition. But if our objective function has quadratic or linear or whatever objective function, we don't care if the first derivative is continuous or not, then we can go for ALR, augmented version. And as I said, both of them as a heuristic implemented successfully to mixed integer problems like unit commitment. Good. Any questions so far about the background of LR? Is it clear so far? Yes. Jemima and Hosna says yes. Very good. Let's say we have this original linear problem. Let's say it's yeah. So we have this problem. Do we have complicating constraint here? It's not necessarily linear. I mean, even it could be convex, but quadratic or whatever. Do we have complicating constraint or constraints? Is this problem decomposable? Carolina, let's say, is last two. Ahmad says the same. Libai says the same. So Carolina, why the last two? They are complicating constraints?
Because they are a summation for every I.
Mhm.
They didn't link
If
all
I eliminate them, what happens?
the problem. You can solve the problem for each I.
Exactly, exactly. If I eliminate them, I can solve the original problem, one per I. Very good. Yes, it's decomposable. The last two, they are complicating constraints, and lambda and mu, they are corresponding dual variables. Good. So remember from lecture number 1 that we can write the Lagrangian function of the corresponding problem, which is this. In this case, what we write is partial Lagrangian function. It means that we keep the original constraints that we don't, I mean, we keep them there, just we bring the complicating constraint to the objective function. So this is the partial Lagrangian function. It's totally fine. So Lagrangian partial Lagrangian function is still constrained, while the full Lagrangian function is unconstrained problem. It's okay, no problem. And if you remember to take the dual problem, we need to go for maximization. So max over the dual variables, mean over the primal variables, partial Lagrangian function with respect to original constraints is exactly equal to our original problem. Is it clear? So what I did, I bring this to constraint to the objective function. So now in our objective functions, we have a term with lambda and mu. They are dual variables. So I'm writing max over lambda and mu. So it's a max min problem. Is it clear? Very good. So this max min problem, it's equivalent to our original problem. Is it decomposable? Can we decompose this problem per I? Carolina and Brian says no, and I agree, because now still we have a terms that links all i's together. It wasn't constraints, now they are in objective function. And as you see, lambda and mu, they are not I index. If they were I index, then we could do something, and also m and n, but they are not I indexed. So this problem is not decomposable. Good. Sorry, not yet. Okay, let's go for a trick. What if we relax the the partial Lagrangian function? What do I mean by relaxing the Lagrangian function? What, instead of lambda and mu as dual variables, what if I fix them to lambda bar and mu bar? If I do that, then the maximization problem is gone, because I've fixed lambda and mu to some given values. We are not optimizing them anymore. So we don't have maximization term there. Lambda and mu as dual variables, now they are treated as parameters. Now, is our problem decomposable? Any clue? Any answer in the chat box? Akilas says yes. Akilas, how? Also, yeah, I got answers.
Well, now since lambda and mu are fixed, so they are parameters, we can just do the multiplication, and we can see that there are no, let's say, coupling constraints nor variables.
Yes, yes. What about m and n?
These are Now they are constants.
Yeah, lambda is constant, m and n, they are constant, so we can remove them, right? So exactly. So we have one subproblem per I, right? Now, by fixing lambda and mu, I can decompose this problem, this relaxed problem, 1 per I. Do you agree, Aklas?
Yes, I agree.
Good, good. So directs it only if we treat xj not equal to I as parameters. Okay, so, okay, directs it, no, I understand now, good. John says, so you are considering lambda and mu as complicating variables, right? Yes, but they are dual variables. Yeah, you can say the dual variables, now they are complicating variables if you like. But remember, they are corresponding to complicating constraints. So instead of saying that I'm fixing the dual variable, I'm saying I'm relaxing the primal constraint. This is why I call it relax. And this term relaxation, Lagrangian relaxation, comes from here. Very good. So the minimization is gone because I fixed lambda and mu to given mu bar and lambda bar. And now our problem is decomposable 1 per I. So there is no sum operator anymore in the subproblems. And as I said, n and m also is gone because lambda bar times m and mu bar times n, they are constant, can be removed from the objective function. Very good. LR is a very iterative, it's an iterative approach with a systematic way to update the values of fixed dual variables, lambda bar and mu bar in each iteration. So it's a really, really simple technique. So for each iteration, for given lambda bar and mu bar, you solve them. And then in each iteration, you need just to update lambda bar and mu bar, nothing else. This is why we call it also dual decomposition. Okay, how to do that? We have different techniques to update lambda bar and mu bar over iterations. You can read this very nice paper from 1999. There are different techniques how to update lambda bar and mu bar, like subgradient methods, cutting plane, bundle method, and trust region methods. In this paper, there is a very nice comparison of comparison of their performance. But remember, LR works only and only if f of this function is quadratic. It's continuously differentiable. If it's linear, LR will not work. Then we will talk about augmented Lagrangian relaxation. So if your original objective function is quadratic, you don't need ADMM. You don't need augmented Lagrangian relaxation. Just simply solve your problem with Lagrangian relaxation, or other words, dual decomposition. How to update dual variables over the iterations, one of these techniques. Is it clear so far? Good. I'm not gonna present this paper. Also in the book chapter, there's a good description of all 4 techniques, but the simplest one, but maybe the most naive one that you may need more iterations is the subgradient method. Okay, let's go for an example. Our original objective function is quadratic. Good, so we can, and convex, so we can use dual decomposition or Lagrangian relaxation. Good news. And we have only one constraint. We can say it's a complicating constraint. It's a very simple problem. You can even solve it directly, but we implemented dual decomposition just to learn how it works. You remember definitely. So then you can write your problem equivalently with max mu, mean over x and y, x squared plus y squared plus mu minus x minus 5 plus 4, right? Then we fix the dual variable, so this term is gone. Then this is just mu bar. Then you can simply say this is decomposed to mean over x s square minus mu bar x, and also mean over y squared minus mu bar times y. And the term for mu bar times 4 is gone because it's constant. Lisandros asks, can we use LR if the objective function includes constant cost using binary variables? No, the original objective function should be continuously differentiable. So if it has binary variables, we can't do that. We should be able to differentiate and the result should be continuous. That's the only condition LR works, because it's based on the gradient method. So we have two subproblems. So for initial mu bar, you can start solving these two subproblems separately, in parallel, not sequentially, in parallel. And you obtain the value of x and y. What to do? You need to update the value of mu bar in iteration nu plus 1. So let's say that how we can update it. It's the simplest method that you can go for, subgradient method. So for given a and b, for example, in the book, in the example of the book, it's a is equal to b 1, b is equal to 0.1. This is the constraint you relaxed. So the original constraint you relaxed and its absolute function, it means that this term gives you either plus or minus times to a weight. Just simply, you are going, so if you start from mu bar equal to 1, next step you will go to, I don't know, 1 plus something or 1 minus something, depending on the sign you achieve, and you go towards the optimal solution. And definitely, if this term, let me raise it, depending the values of a and b you took, you may have a big jump or small jumps. Is it clear? Yes. It's a kind of a simple approach, but if you like to update, so Lagrangian relaxation works better if your update approach for mu bar is more elegant. This might not be very elegant. So what I like you in exercise, you will code for tomorrow, maybe for different values of a and b that, how to say, assigns or updates your jump, or I don't know what to say. You can check how with different values of this weight, you get convergence. With the higher iterations or less iterations, you can try it out. A step size, thank you. Step size. Good. And if you are really, really interested, also, I suggest you to go through other approaches to update mu bar. Good. What is the stopping criteria, you think? When do we know that we got convergence? How to know? We continue these iterations, but how to know that we reach to convergence? Any idea? You can write in the chat box. One idea is change in value of objective function is smaller than some value eta. Yeah, but maybe we have something. Jan says when the duals don't change anymore. That's a good one. I go for that. Yes, Achilles said check whether constraints are violated. Exactly. This is the constraint we relaxed. So we can check if that constraint is hold or not. So in the paper of Boyd, they go for both checks, dual and primal checks. But for ADMM, I'm not sure for LR we need to check both of them. The primal check is that just check the residuals in the complicating constraint we relaxed. So whenever this constraint is hold or the residual is very, very low, it means that minus x minus y plus 4. Okay, it's not equal to 0, but I don't know, 0.00 something. Then we can say that we converge from primal aspect. Also, dual means that we check the evolution of mu bar, and the mu bar over the iterations should reach to a certain, let's say, value. It's not changing over iterations anymore. Sebastian says, but surely that's just feasibility. What do you mean, Sebastian?
I mean, you just said that we're checking the value of the constraint, but if we're only checking the value of the constraint, that's feasibility, that's not optimality.
Yeah, for LR, for ADMM, yes, maybe not for LR, but yes, I agree.
I mean, so how do we check whether we've hit the optimal point as well? Because surely we need that check too.
But Sebastian, we are updating X and Y. So our values for X and Y, they are optimal definitely, while the constraint is hold. So it's not just feasible, but also it's optimal. Or am I wrong?
I mean, there are many values of X and Y that will fulfill that constraint. The feasible region is not just a single point. I mean, the feasible region has more than one possible value.
But the problem is quadratic. We have uniqueness.
Uniqueness of solution, but not uniqueness of feasible solution.
No. But since X and Y, they are quadratic, it means that our solution with respect to X and Y is unique. Am I wrong? So you don't have multiple solutions for X and Y.
I can definitely think of multiple feasible solutions to this problem.
Yes.
They might not minimize the problem, but that's my point. So how do we check that the value that we've put in also minimizes, but doesn't just...
But we are optimizing X and Y or the subproblems. We are not just selecting the feasible.
Yes, but I want to optimize it over not the subproblems, but the main problem. And that's my question. I don't know where we're checking that it's the optimal value yet.
Okay, I'm not sure I'm answering correctly, but this is my answer. I think since we are optimizing in the subproblems, while we know that the constraint is fulfilled, and while we know that we have a unique solution for X and Y, if we get convergence, it's the optimal solution. That's my understanding. Yannick says, but X equal to, okay. Hosna says, but all the subproblems are minimizing their objective as well, so the feasible can be optimal. This is what I'm... Hosna, maybe you can unmute and elaborate what you're saying.
Yes, I think we have two positive variables. So if we minimize each of them, the total problem is minimizing. So if in each subproblem we minimizing each variable, so if we get the optimal, get the feasible solution considering these constraints, so I think we get the optimal solution as well.
Okay, good. Thank you, Hosna. Do we have any other observation about this problem? About what Sebastian asked? Other Sebastian says, because we start from mu equal to 0, so we will start from the most optimal point with the constraint not binding. Shall you elaborate? You're welcome to unmute and explain.
Yes, because we are solving the subproblems in the first step with an initial value for mu, right? So I assume that we will start from 0. So in that case, we are basically... Sorry?
We don't,
yes, of course.
Yeah, we don't need to start from mu bar equal to 0. It's just, we can start with any point.
Okay, yeah, then but that changes somehow. So I'm assuming that we start from 0. So that would mean that the constraint is not binding, right? Because if the dual variable is 0,
Not
the constraint will not be
necessarily.
binding.
Yes, yes. You can start with anything you like. It's not necessarily to start from 0.
Okay, all right. So I guess my reasoning was that if we start from 0 and the constraint is not binding, if it's binding, we'll update the mu. So then we'll move to a less, let's say, we will constrain our problem more. So we'll, in the first solution, have the most optimal solution already, considering that the constraint is not binding, and then we'll update our solutions along the constraint. So that's my explanation why we're considering the most optimal point.
Thank you. Thank you. Good. Let's continue. So yeah, here we check the change of mu. Also, I would say we have to check the residual value for the constraint. So that's what should I also add to the slides. So as exercise, please provide a code. It could be whatever in GAMS or Python or Julia for this example, and try different step size and see how does it impact your convergence rate, your convergence speed. Cool. Let's now talk about ALR, the Augmented Lagrangian Relaxation. Do we have any question left from LR? Is everything clear? If you write in the chat box, everything is clear, I can move on. Good. So ALR works for the problems that we have either quadratic or, I don't know, linear objective function. If we have original objective function linear, then we have to use augmented Lagrangian relaxation. What does it mean? It means that, so if we have objective functions of the original problem, f of x subject to whatever, and we know that f of x is linear, we need to add additional penalty to the original objective function. That penalty, what do you think? Should it be linear? Should it be quadratic? Should it be whatever? What do you have any idea? Let me continue. Maybe I can provide a better. So I'll get back to that question a bit later. Do the original, we go for the same, yeah, Nuran says quadratic maybe to be smooth. I'll get back to that point. I'm using the same example just to be able to compare it with the previous problem. But since the objective function is quadratic, even you don't need to use ALR. But if you like, you can also use ALR. So here, the objective function could be linear or could be quadratic. Well, again, we saw that we can, this is our dual problem. So remember that if this problem was linear, it means that our Lagrangian function is linear, while our Lagrangian relaxation technique is based on the dual variables. It's based on the gradients. If our original objective function, let's say it's something like this, this is the original objective function or whatever with respect to our variable, if only we have one variable, right? If it's linear, it means that its gradient, the slope, will not give us any idea in each point. Should we go up or down? No idea. But if we go for a quadratic objective function with respect to a single variable, the slope gives us an idea. It's a gradient descent, which direction we should take. So this is why Lagrangian relaxation works if our original objective function is quadratic. Is it clear? But if our original objective function with respect to our variable, if it has a linear profile, Then, for example, we start from this point, we get a slope, but we have no idea which direction we should go in the next iteration, because a slope in all over of this space, feasible space, is equal. Is it clear? So always, to be able to use dual base technique iteratively, we need to have objective function quadratic. It's either originally quadratic. If not, we have to make it quadratic. Clear? Good. Now let's explain like this. Let's say our objective function with respect to one of the variables, let's say we have only one variable, has this kind of plot, and we know that this is the optimal point. We are minimizing our objective function. Now we like to make it quadratic to make sure this gradient based method will work out. So what we need to do is to make it quadratic, but not changing the optimal point. If I make it quadratic, but the optimal point is different, then I'm not solving the same problem. I need to make it something like this. So instead of the original problem, which is linear, I'm solving the augmented problem, but with the same optimal point. So that's the whole idea of augmented Lagrangian relaxation. So the question is that, how can I go for this quadratic problem corresponding to this original linear problem while making sure that the optimal, I'm not changing the optimal point? How can I do that? So the question is that I need to add something quadratic, but making sure that the optimal value for x and y will not be changed with respect to the original problem. So what do you suggest to add here? Is my question clear? So I would like to build a quadratic counterpart for my original linear objective function while making sure that my original optimal point will not be changed. So I need to add a regularizer, if you like, or a quadratic penalty term while making sure the optimal value of x and y is not changing. So what this term should be here to be added? Ahmad says a square of the added term. Which added term, Ahmad? You're good. So this is my original constraint. I know that in the optimal point, it's equality condition. I know that in the optimal point, it's equal to 0. So if I add the same term, but in the quadratic form, am I changing the optimal solution? No. Because in the optimal point, I'm talking in the optimal point, the value will be equal to 0, like this, right? While, so I'm minimizing the original problem, while in the optimal point, the rest of the problem will be equal to 0. So I'm solving the same problem. And the good thing is that now my augmented Lagrangian function now is definitely quadratic, irrespective of this first term, original objective function is quadratic or not, linear or not. I don't care now it's linear or not, because I intentionally added a quadratic term. Yes, Drake, please.
So that makes sense that it would be 0 at the point of optimality, but there are other points that are not optimal where the constraint could also be met. So then wouldn't you be guided down a slope towards those points as well?
Can it happen? If it happens, then our problem is not convex, right? It means that we have multiple solutions. And we have a local solutions. If we have this kind of profile for our original problem, I agree, we may end up to here or here. But if our problem is originally convex, it will not happen, will it? Drake? I don't think it will happen. It's not the case if our original problem is convex.
Okay, thinking about that.
That's my impression. Is everything clear so far? Maybe you can write clear in the chat box. You said what is this norm? Yes. So if we have x and y as a if we have a vector of variables x, so exactly this is norm 2, it means that it's equal to, let's say, x. So if it's a vector of, I don't know, x1, x2 till xn, so it's just x1 square plus x2 square, blah, blah, blah. And since it's a square, then this square root is gone. So it means that for every single variable or yeah, the complicating variable you need to add. For example, let's say you have two complicating constraints, like here minus x minus y plus 4 is equal to 0. And also you have another equality. Let's say, I don't know, x plus y plus 3 is equal to 0. Not something like this, but yeah. Then you need to add two of them. So minus x minus y plus 2 square, right? Yes, exactly. Yes. Plus the other one, x plus 1 plus 3 square. Right? With their corresponding dual weights. Anyway, Kelly said, sorry, I'm confused. We did not need to add the penalty term in this case. Here, in this case, you mean, Kelly?
I mean the last term. For this example, it was not required. We could have applied the original Lagrangian relaxation, right? With this objective function, I mean.
Yes. I'm not sure I got your question, Kelly, to be honest. Which example you mean?
This, I mean, with this objective function.
Yes. Since
yeah.
it's quadratic, we don't need that. But I kept it quadratic to be able to compare it with the previous example. Yes,
okay, thank you.
Since this is quadratic, no, we don't need to add it because our original function is already quadratic. But if we add it, it's not wrong. Right? Nice. Very good. Good. You did not ask a question. Here, I assume that my complicating constraint is equality. Yes, Lorenzo exactly asked that question. What if we have G of, if we have a non-equality, can we, and it's a complicating constraint, what should we do? Can we do this trick? If our complicating constraint is inequality, can we go for this trick or not? Not anymore. No, that's the point. If we have inequality constraint, my understanding, we cannot directly use ADMM. We need to add slack variables to the original problem. Let's say plus mu, which is a slack variable, now is equal to 0. And then to penalize mu as a slack variable in the objective function. So we make inequality an equality, and then we can use augmented ALR. Exactly. Neuron and Lorenzo also mentioned that by slack variables, we can make inequality equality, and then we can use augmented Lagrangian relaxation technique. Good. Let's continue. We are over time. The time is over. Good. So we talked about why we need this term, quadratic term. So Brian talked what about this gamma? It's a constant, but what should it be? We'll talk about it later. So now, like Lagrangian relaxation, let me fix lambda to be lambda bar, and then this maximization problem is gone. So now is our problem decomposable or not? In Lagrangian relaxation, it was decomposable. But what about now? Is the question our optimization problem with lambda bar, is it decomposable 1 per y, 1 per x? Drake says not linearly. What do you mean? Means no. Why not decomposable?
Well, if let's look at x and y being scalar, then we'll have an xy term in the objective.
Yes. So if we open this term, we have a term of x times y. It means that our problem is not decomposable anymore. Yes. So this penalty term, quadratic term, it's nice that we added. So now we can use gradient-based methods, but we lost the decomposability of our model. That's the cost it comes. So what to do? We have two techniques for ALR, APP and ADMM. I'm not going to go with APP, but the whole idea of APP is how we can approximate, what was the term? Sorry. How we can approximate this quadratic term with some term that in which x and y, they are separate, we can decompose. So APP is an approximate technique. So you approximate this score technique with something which is decomposable. But you can go and read how we can do that. But ADMM is a very simpler technique. So we have this term minus x minus y plus 4 square in each iteration. Do you know what ADMM says? Any idea? ADMM comes with this term, alternating. Any idea what we are going to do in ADMM? Remember, in iteration I, we have in objective function this term, minus x, in iteration I, minus y, in iteration y, I plus 4 square. Alternating, what does it mean? Yes, Lorenzo, fix x or y. Exactly. So in iteration I, we fix x to something, let's say something, 2 or whatever from the previous iteration, and then we solve y, and other way around. So in each iteration, we consider one of them parameter coming from the previous iteration and solve for y. And now we assume y is constant, its value coming from the previous iteration, we update the value of x. I'll explain more. So in ADMM, it's a really simple approach. We directly fix each variable to its value obtained from the previous iteration, and we decompose the ALR problem. So before talking about the convergence proof, let me show what we are going to do. So this is our original problem. We go for lambda bar, so we eliminate maximization. So what happens? So now with ADMM, we have X update subproblem and Y update subproblem. So X in iteration new, it's a variable. This is not variable anymore. So it's gone. Then from this term, lambda is lambda bar coming in from the previous iteration, new minus 1, let's say. After, at the end of iteration new, we will update lambda. Y is fixed, 4 is fixed. The only remaining term is x. So here is minus lambda times x. Now from this term, gamma is given. Minus x is our current variable in x update problem. I call it x update subproblem. Y is a parameter comes from the previous iteration, and 4 is the same 4. Now this problem is linear in x. And we do the same for y. So now this in y update problem, y update subproblem, x is given while y is variable. Is it clear how it works? Is it clear? Good. So here, as you see, when we go for x update problem, y comes from the previous iteration. And when we go for y update problem, do we have x in iteration new, but still we go for the previous x in the previous iteration? Does it make sense or not? Shall I write it x in new, or should I keep it x in iteration new minus 1? Any pros and cons? Is question clear? Nicholas says x new converge faster. Priyanka says to solve simultaneously. Okay, two very good answers, but if we put them together, what are the pros and cons? That's the point. If I like to solve y update problem and y update problem simultaneously in parallel, I need to get their values both from the previous iteration, like here. But if I like to converge faster, it's always better to use most updated information. Then it means that first I know I need to solve x update from given the y value from the previous iteration. Then sequentially in the underlying iteration, I solve y update problem. I cannot solve it in parallel. It should converge faster because you use most updated information, but you lose the capability to solve x and y update problems in parallel. So it's up to you which one to use, depending on your problem. Is it clear? Yes. Okay, what about lambda, the dual variable? It's simple. Our lambda in the current iteration is the one in the previous one plus the same gamma that we had times our complicating constraint. So in the optimal point, this term is equal to 0. It means that the value of lambda is not changing anymore over iterations when we reach to convergence. Again, here, based on the Boyd's paper, we have to check both lambda and the convergence of the lambda. Also, we need to check the residuals of the complicating constraint. Both of them, they should be converged. And of course, they are the same thing, right? Yes. Yes. Any question? Is it clear? Good. So algorithm, we do it until complicating constraint is not changing anymore. The very tricky things in ADMM is tuning gamma. It's not that very, easy what to do. in Boyd's paper, there are some tips how to dynamically update gamma. You don't need to keep it constant over iterations. You can use, I don't know, updating dynamic techniques, dynamically change the value of gamma over the iterations. You can do that. Or if it works, you can say always my gamma is 2 or 20 or whatever in all iterations. But always it's nicer to find elegant ways to dynamically change gamma over the iterations. Definitely, I mean, in the first iterations, this value is far from 0. So you have to think what you like to be gamma. If also gamma is big, while also this term is big, then the whole term is very big value. So maybe in the first iterations, it's better to go for small values for gamma. And then over iterations, when this complicating constraint is getting closer to 0, maybe you can go for a higher value for gamma. But in general, for ADMM, the most challenging thing is to find how to tune gamma. And there is no optimal way for that. It's all, based on your, it's case specific. You have to see for different gammas how, your model works. Am I clear? Is everything clear? Good. So please also write a code in GAMS or Python or Julia or MATLAB or whatever, this time for the same example, but using ADMM. So here you can play with the value of gamma. Maybe you can put a small value for that. Next time, big value. Maybe next time you try to make it dynamic. Start with the small values in the first iterations and then starting increasing the value of gamma and then to compare the number of iterations. So that would be amazing if tomorrow you show some plots of convergence of ADMM with respect to different values of gamma, either static gamma or dynamic gamma over the iterations. So that's it. So you have 2 exercises for tomorrow, but let me now talk about the convergence. So let me provide some references for you. For convex problems, under some certain assumptions, for example, the problem should be convex, optimal point should exist, Slater conditions should hold, the objective function should have first derivative continuous, or it should be continuously differentiable for LR, for LR, not for ALR, sorry. But still the original objective function should have continuity. We call it Lipschitz continuous. I'm not going to explain what it is. Under some certain assumptions that you can check from these papers, we have proof of convergence to global optimal point. So there is a proof in Boyd's paper, Boyd's et al. Paper. You can check convergence proof in Appendix A of that paper. Also, there's a very nice paper by Hong and Liu. It's also about the linear convergence of ADMM. They again talk about the assumptions that we need for, or conditions under which the ADMM converges to global optimal solution in terms of if our original problem is convex. Also, this paper analytically explains the convergence rate. And kind of shows that ADMM in terms of convergence rate is not very amazing. The convergence rate is linear. It's not quadratic. Then for non-convex problems, of course, we don't have a proof of convergence to global solution, global optimal point. But under, again, some assumptions, we have a proof of convergence to local or stationary optimal point. The local point or stationary point. So there are very nice papers again from Wang et al., from Hong et al. But I liked very much this paper from the group of Professor Andy Sam from Georgia Tech. They applied ADMM to an AC-OPF problem and argued and proved the convergence in general, but not necessarily to global solution. And also there's a very nice video lecture by Professor Andy Sun in University of Cambridge about distributed AP-OPF. It's a video lecture of reference 3. So I suggest that you can, I mean, if you are interested in ADM, you can check out these references. Yes, that's it. So thank you so much for your attention. We are really, yeah, out of the time. The time is over. So is there any question, or maybe you can tell me the content of the course, the lecture, was it clear or not? There are some questions here and there. Any question? Was it clear? Good. So Saurabh says there is a paper that shows convergence to the global solution for ADMM for 2-stage mixed integer program. Thanks, Saurabh, for sharing the link of the paper. Okay, so for tomorrow, you have 2 exercises. Both are coding of LR and ALR. For LR, please try to change the step size and see how the number of iterations change. Also for ALR, please play with gamma, make it static, but big value or low value, relatively small value, or please make it dynamic over the iterations from small values to big values over the iterations, and then compare the number of iterations. And we will talk about it tomorrow in the exercise session. If any question left, I'll answer it tomorrow. Thank you so much and see you tomorrow afternoon. Ciao.